So I'm going to solve three generic initial value problems. For you, y naught was always 2. Well, let's see if I can do this with arbitrary y naughts. I'll work from right to left. Let's do this one first. In each case, we're going to separate variables. If we separate variables for the differential equation, we get dy over y squared minus 1 equals dt. We want to integrate both sides, but to integrate the left side, you want to use partial fractions. Y squared minus 1 can be factored as y minus 1 times y plus 1. And we want to write that as the sum of two fractions, a over y minus 1 plus b over y plus 1. We want to solve for a and b. So multiply both sides by y squared minus 1 to completely cancel it on the left and get partial cancellation on the right. In other words, I'm multiplying by y minus 1 times y plus 1. The y minus 1 cancels with the a term, leaving a times y plus 1. And the y plus 1 term cancels with the b1, leaving b times y minus 1. To be extra picky about solving for a and b here, technically you should expand this and get something times y plus some constant and get a system of equations in a and b. Okay, that's a lot of work. There's a shortcut that helps here to solve for a and b more quickly. Maybe you'll learn this in Calc 2. If you substitute, for example, y equals 1 into both sides of the equation, the b term goes away and you can easily solve for a. A is going to be 1/2. You want this equation here to be true no matter what y is. So if we pick special values of y, like 1 and -1, we can solve it for those special values of y, and it does turn out that that makes it work no matter what y is. Maybe that's not obvious, but it is true. If I pick y to be -1, the a term will go away. I'll get 1 is -2b, so b is -1/2. So coming back to the differential equation where I have to have it in separated form and I have to integrate both sides, I'm going to end up doing the integral of a is +1/2. I got +1/2 over y minus 1. B is -1/2, so that's -1/2 over y plus 1. Integrating 1 on the right side gives t plus, say, c1. This is going to give 1/2 ln of the absolute value of y minus 1 minus 1/2 ln of the absolute value of y plus 1. I think it does turn out to be a little simpler if you multiply both sides by 2 first. Turns out to be a little simpler that way. Then we don't have to bring the 1/2 into the exponent. So multiply both sides by 2. Then combine the logarithms into one logarithm. The difference of two logs is the log of their quotient. So I can write this. And 2 times c1, I'll call it c2. Exponentiate now to get rid of the logarithm. Can I get rid of the absolute value signs? Well, it always seems like we can, so why not go ahead and do it? Is there ever a case where you can't? I don't know if I've ever encountered one, but it's kind of good to be careful in general. Here I'm using C3 to represent really, well, e to the C2, and then maybe the absolute value of C3 equals e to the C2, and then I get rid of the absolute value signs because I got rid of them on the left side. C3 could be positive or negative. So now I'm getting close. I have an algebra equation now to solve for y. Cross multiply effectively. We'll get rid of the fraction. This is over 1. In other words, multiply both sides by y plus 1. Y minus 1 will be this thing times y. And then that thing times 1 is just itself. Isolate y, so now subtract that from both sides, add 1 to both sides. I'll also factor out a y after subtraction. Hopefully I haven't made a mistake. Now just divide both sides by this. Got the constant C3 in two places. Should I just call it C, or should I sort of finagle this to try to get it? That's just one C in one spot. That's not so clear. I'll just call it C now. So the constant C, unless I massage this in some way, it seems to be appearing in two spots. I didn't know that was going to happen. Okay, I don't think I've made a mistake. So look good to people. Is this okay? I think it's okay. You set t equal to 0 and solve for, and y equal to 2 and solve for C. I'm going to see if I can do it for a generic initial condition. Why not? Plug in C equals 0, e to the 0 is 1, so I get this. Yeah, I think I'll be able to do this. Your y naught was 2. Again, cross multiply both sides by 1 minus C, get y naught minus C y naught equals y plus C. I'm trying to solve for C. Y naught minus 1 will be C times 1 plus y naught, it looks like. I did a couple steps in my head there. Subtracted 1 from both sides, added C times y naught from both sides, and then on the right factored out a C. I guess I did three steps. So C looks like it's y naught minus 1 over y naught plus 1. Your y naught was 2, so maybe you got 1/3 for C. Okay. We can now plug this back into here, there, and there. We could, it probably is beneficial when doing so to, we have fractions within fractions here, to try to get rid of the fractions within fractions by multiplying the top and the bottom by y naught plus 1 to cancel that bottom fraction. And if you do so, and if you want to use the phi notation, not that anybody probably did, what it looks to me like you'll get, I'm doing a bunch of calculations in my head here, is y naught plus 1 plus, in parentheses, y naught minus 1 times e to the 2t divided by y naught plus 1 minus, in parentheses, y naught minus 1 e to the 2t. I replace the c with that, and then I multiply the top and the bottom by y naught plus 1. Hopefully no mistakes. Okay, so this solves any initial value problem. What about the phase line? That's where you want to come back. I will show that to you if you were writing it down again. That's where you want to come back up and think about this qualitatively. The right-hand side function, call it f of y. It's still good to think about the factored form here, y minus 1 times y plus 1. Remember, with a phase line, you're trying to essentially take a slope field and mash all the information onto just the y-axis. It only should be done with autonomous equations where the right-hand side has no t's. Don't do it if it's an f of t on the right. Don't do it if it's an f of t comma y on the right. Only do it if it's f of y, an autonomous first-order differential equation. Because if you do it, if it involves a t, then the slopes are not constant along horizontal lines in the slope field. And so mashing it onto the y-axis doesn't make any sense in that case. But when they're constant along horizontal lines, then you can do that. And can I draw this phase line without actually drawing a slope field? Think first about equilibrium solutions. Where is the right-hand side 0? Well, 1 and negative 1. Those become equilibrium points on the phase line. 1 and negative 1. What do you want to do for the rest of the phase line? You want to draw arrows indicating whether solutions are increasing or decreasing. How do you do that? Once again, think about this right-hand side function, and if it's helpful, and it often is helpful, draw its graph. I'll make just a little graph up here. It's a parabola opening upward with roots at 1 and negative 1. Here in this picture, the y-axis is horizontal. Down here in this picture, the y-axis is vertical. It's okay. It's just helpful. That's all it is. I can more easily see where this function, the right-hand side, is positive and negative. Where it's negative, when y is between -1 and 1, that means for solutions of the differential equation, dy dt is negative. Slopes are negative. So you have to have decreasing functions in the slope field when your initial conditions are between -1 and +1. So draw a downward pointing arrow. Over here, when y is bigger than 1 or less than -1, f of y is positive. Dy dt is positive for solutions of the differential equation. They're increasing. So we use upward pointing arrows. Oops, mistake. Upward pointing arrows. This is telling us the long-term behavior of y based on initial conditions. If the initial condition is bigger than 1, y goes off to infinity as t increases. If it's between 1 and -1, it goes down to -1 as t increases. And if it's less than -1, it goes up toward -1 as t increases. When nearby solutions head toward an equilibrium point, it's called a sink. When they go away from the equilibrium point, it's called a source. Should you imagine like water molecules along here going toward the sink or away from the source? Well, if you want, for fun, that's just for fun. It's a nice visual, okay? Yeah, most of you probably worked on this the whole time. I wasn't thinking about how complicated this would get. Yeah. Mm-hmm.
Yeah, you could draw a horizontal phase line.
No, because you're still interested in y. You just don't want to draw a phase line at all if the right-hand side involves any t's. Yes, you can think about what happens to individual solutions, but sometimes they go up and down if the right-hand side depends on t. With autonomous equations like this, they're either always going to go up or always going to go down or always be horizontal. That's why you want to stick to this kind of thing. Can I do the other ones quicker? I think so. I think I can do these other ones more quickly. We get this. This is the same as y to the -2 dy. Integrate both sides. Get y to the -1 over -1 equals t plus c1, say. No logarithms here. Multiply both sides by -1 and take the reciprocal. So I'm doing 2 steps at once here. And -c1 is going to become c. Yeah, this will be quicker. Y naught equals y of 0 equals, it would be 1 over c. So c is going to be 1 over y naught. So if you got to this one, when y naught is 2, you should have gotten 1/2. But if I'm going to write the unique solution of a generic initial value problem using my phi notation, I could write this, though that doesn't include the equilibrium solution at y naught equals 0, because I'd be dividing by 0 there. So I can try to get rid of the fractions within fractions here by multiplying the top and the bottom by y naught and doing a little rearranging. That's a better way to write the solution because it does include the equilibrium solution when y naught is 0. And yeah, the right-hand side is just y squared. If I draw f of y here, it's a parabola opening upward, just touching the horizontal y-axis here. For the phase line, there's only one equilibrium solution and therefore only one equilibrium point, and all other solutions are increasing because f of y is positive. So dy dt for solutions, the differential equation is positive. Hey, that's not a sink or a source, is it? It's a sink from below and it's a source above. So it's neither. It's a node, it's called. What about this one? Separate variables, dy over y squared plus 1 equals dt. Integrate both sides. Arctangent, or if you prefer, inverse tangent of y equals t plus c1. If you prefer using arctangent, that's fine. Arctangent and inverse tangent are the exact same function, just different names and different notation for the exact same function. Calculators use inverse tangent symbol. Mathematica turns out to use arctangent symbol. Solve for y by taking the tangent of both sides. And maybe I should just call it c instead of c1 because there's not much you can do with that. I mean, yes, tangent of a sum does equal, there's some identity that says it's equal to something, but I think it's going to be more complicated. I think it's better to leave it like that. For generic initial condition, looks like the C is going to be arctangent or inverse tangent of y naught. So if you got to this one, you would have got an inverse tangent of 2. Which, if you're in radian mode, which you should be as a default, inverse tangent of 2 is about 1.107 radians. But you don't have to think about angles. You're just thinking about functions here. It's 1.107 is an approximation for the C you would have gotten when y naught is 2. So if I'm writing my phi notation, I would say the unique solution is tangent of t plus, in parentheses here, inverse tangent of y naught. So that would be the answer. And there's nothing you can really do to simplify this, I don't think. This is about as simple as it gets. You can't say it's tangent of t plus y naught or something. Tangent doesn't have that kind of property. How about the phase line here? Y squared plus 1 is the f of y. F of y has a graph that's always above the horizontal axis. So for the phase line, there are no equilibrium solutions, and all solutions head upwards. So we're in a situation where, these are related ODEs here. Y squared plus something, plus or minus something. You can think of this as a plus if the constant that's being added is -1. All these ODEs are of the form dy dt equals y squared plus something. I'm going to call this something mu because it's a common letter to use. In this case, mu is -1. In this case, mu is 0. In this case, mu is +1. Depending on the value of mu, we have a different method for solutions giving different formulas. And we also have different phase lines. Here we had a phase line with 2 equilibrium points, one a sink, one a source. When mu was 0, we had 1 equilibrium point, a node. And when mu was 1, no equilibrium points. Makes sense because the f of y graph goes up as mu increases, and it initially had 2 intercepts when mu was negative, to exactly 1 intercept when mu is 0, to no intercepts when mu is positive. This is a big subject coming up in coming lectures. It's called, what happened here is called a bifurcation. The number of equilibrium points, in a sense, bifurcates from, well, if you let mu run backwards from positive to negative, from 0 to 1 to 2, bifurcates meaning 2, it's like a fork. We've gone from no equilibriums to a fork of 2 equilibriums when we draw something called a bifurcation diagram. And I think I'm not going to take the time to explain that today, but it's something to watch out for. Another thing to watch out for in the differential equations portions of the lectures is something called linearization. Something called the linearization theorem. That, for example, in this example right here, this case, helps you predict you got a source here and a sink here based on the derivative of this function at the equilibrium points. The fact that this one's positive and this one's negative for the derivatives. the slope of that curve, implies this one's a source and this one's a sink. That's what the linearization theorem implies. That's a really big deal. It's a minor deal right now. It's a really big deal when we get to chapter 5 near the end of the semester, linearization. We have to apply linear algebra to higher dimensional nonlinear problems. And well, this is going to be a name from multivariable calculus. We have to use something called the Jacobian matrix to help us do it. Jacobian matrix of partial derivatives. You maybe did a Jacobian determinant in multivariable calculus if you had that yet, for doing change of variables with double and triple integrals. The Jacobian matrix is going to be necessary to think about higher dimensional linearization. So you want to understand it in this basic case first.